In quantum nonlinear spectroscopy, a novel approach is proposed that leverages the polarization of a coherent light beam as a quantum sensor. By exploiting the Faraday rotation of linearly polarized light after interacting with a target system, this method enables the measurement of higher-order correlations of magnetic fluctuations. A Mach-Zehnder interferometer is employed to post-select quantum evolution or measurement effects, rendering the correlated difference photon counts proportional to specific types and orders of correlations. Analysis reveals that second-order correlations are detectable under realistic conditions, while higher-order correlations become significant when the correlation lengths are comparable to the laser spot size. This protocol offers a distinct advantage in studying quantum many-body systems, as it allows for simultaneous interaction with numerous particles and utilizes a relatively simple interferometry technique. Notably, the ability to probe many particles concurrently facilitates the exploration of complex quantum phenomena, while the straightforward interferometry approach simplifies the experimental setup. The authors introduce the concept of time-ordered higher-order correlations in quantum systems, which can be formulated using commutators or anticommutators between operators. These correlations are denoted as C eta k, eta 1, where eta k element of plus. Conventional nonlinear spectroscopy measures only one type of these correlations, while noise spectroscopy measures only C+++. To systematically extract arbitrary types and orders of time-ordered correlations, the authors propose a quantum sensing approach called quantum nonlinear spectroscopy, QUEENS. QUEENS uses sequential weak measurements via a spin quantum sensor. The sensor interacts with the target system in a sequence of short periods, with projective measurements of the sensor constituting weak measurements of the target. The coupled sensor-target system evolves according to the quantum Liouville equation. The commutator is decomposed into two terms, corresponding to the target evolving under a quantum force from the sensor and the sensor evolving under a quantum force from the target, backaction. After the interaction, the measurement of a physical quantity λj of the quantum sensor at time tj leads to a reduced density matrix of the target. The correlation of the physical quantities measured at time t1, t2, tk can be written as g, k, equals trb, mk, m2 m1, rho b, t0. The initial state and measurement basis of the sensor can be chosen to pre- and post-select the effect of the sensor-target interaction in each measurement period. However, the requirement of a central spin as the quantum sensor limits the versatility of QUEENS. An alternative quantum sensor is proposed: the polarization of a coherent light beam. This has the advantage of large coherent length and ease of preparation, control, and detection. The light beam interacts with the target system, resulting in small Faraday rotation, which is measured using a Mach-Zehnder interferometer. The authors propose a scheme to measure arbitrary correlations of a quantum spin system using a polarized light beam sensor. This scheme employs a Mach-Zehnder interferometer, where the polarization of a light beam is measured in a designated basis by choosing a certain relative phase shift between the two arms. A sequence of linearly polarized laser pulses is applied to a target system, and the light polarization acts as a quantum sensor coupled to the spin system. The interaction with the spins leads to a Faraday rotation of the light polarization, which is then measured in a selected basis. The light polarization is represented as a pseudo-spin 1/2 using Jones vectors, and 3 photon operators are defined to satisfy the same commutators as spin operators. The correlation among a sequence of difference photon counts corresponds to a certain correlation in the target spin system. The signal-to-noise ratio for the measurement of correlations is analyzed, and it is shown that the scheme is feasible under realistic conditions. The correlated photon counts of a sequence of measurement shots, each with a designated phase shift, can be made proportional to a designated type and order of correlation of the spin fluctuations. This is achieved by inducing a designated phase shift phi using a variable optical delay, selecting the basis of polarization measurement. The authors define the pseudo-spin operators S1, S2, and S3 using photon annihilation operators and photon number operators, which satisfy the commutation relations of spin operators. However, the pseudo-spin operators do not have the same anti-commutation relations as spin 1/2 operators, as described by equations 5 and 6. This scheme enables the measurement of arbitrary correlations of a quantum spin system using a polarized light beam sensor, with potential applications in quantum metrology and spin-based quantum computing. The interaction picture describes the evolution of the coupled system of photons and spins. The spin-photon interaction is modeled using the operator v, t, inducing opposite frequency shifts for left and right circularly polarized photons, causing Faraday-rotation. The system's evolution is approximated over a short period tau, resulting in a state that includes a pseudo-spin rotating under the field B. This rotation is selected by preparing the pseudo-spin in an eigenstate of S1 and measuring the photon polarization in the basis of S2. The measurement induces a superoperator on the bath, proportional to the magnetization of the spins. The quantum force driving the evolution of the target is also considered, and its effect can be measured by selecting the pseudo-spin component S3. The measurement scheme uses a 1-to-1 beam splitter to transform input photon operators into output ones, enabling interference between the transmitted and reflected paths. This setup allows for the measurement of either S2 or S3 by designing the phase shift in the reflected path. The correlations of sequential weak measurements are calculated, showing that the correlated photon count differences are proportional to certain types of correlations in the target system. In this section, the authors calculate the signal-to-noise ratio, SNR, for their proposed method of measuring higher-order correlations in spin ensembles. They first consider the shot noise of photon counts and neglect technical noises, as these would depend on specific experimental systems. The SNR for first-order correlations is derived as square root L 2 alpha tau c plus, where L is the number of repeated sequences of k shots of measurement, alpha is the amplitude of the laser pulse, tau is the time interval between two consecutive shots, c plus is the probability of detecting a photon in the positive channel, and g 1 is the first-order correlation. For k-order correlations, the authors find that the variance of the signal is approximately trail s squared 3 k, where s squared is the square of the spin operator and k is the order of correlation. The SNR for a k-order correlation is then given by square root L 2 k1 alpha k c plus k, which decreases exponentially with the order of correlation. The authors also estimate the signal strength for a target system containing an ensemble of spins, assuming a laser pulse length much greater than the thickness of the sample and a laser pulse duration much shorter than the timescale of spin dynamics. They use LiHo F4 as a specific material system, with a coupling constant G approximately equals 20 radians per centimeter, spin density Ns approximately equals 1.39 times 10 to the 28 cc, and a laser pulse with a focus size of tilde operator 10 to the power of 4 cm. Number of photons NPH tilde operator 10 to the power of 14, and a sample thickness of 1 cm. This results in an estimated SNR of square root L 8 times 10 to the power of 12 times k times 10 to the power of 20. To achieve SNR greater than 1, the number of measurement shots should be L 10 to the power of 5 for measuring second-order correlations, which is feasible. However, for measuring fourth-order correlations, the number of measurement shots would need to be L greater than 10 to the power of 49, making it impractical for any experiments. This difficulty in measuring higher-order correlations arises from the fact that uncorrelated or non-interacting spin ensembles typically exhibit negligible higher-order correlations. Near critical points, higher-order correlations emerge as significant factors in interacting spin ensembles, characterized by collective fluctuations with diverging correlation lengths. The signal-to-noise ratio, SNR, for measuring correlations is modified according to equation 18, which accounts for collective fluctuations and the size of the laser focus spot. This enables the measurement of higher-order correlations when the correlation length is comparable to the focus size. The proposed scheme offers a novel approach to studying the effects of higher-order correlations in interacting spin systems near critical points. Unlike single-spin sensors, which interact with only a few nearby spins, the optical polarization pseudo-spin can uniformly couple to a quantum many-body system, allowing for the extraction of arbitrary types and orders of quantum correlations. While detecting second-order correlations is sufficient for characterizing quantum many-body systems far from critical points, higher-order correlations become crucial near critical points, where collective fluctuations dominate. The optical detection of higher-order correlations becomes feasible when correlation lengths are comparable to the focus size of the laser beam, making this scheme a valuable tool for quantum nonlinear spectroscopy. This approach has far-reaching implications for various fields, including the study of quantum foundations, optimal quantum control, and quantum sensing. As a method of quantum nonlinear spectroscopy, it can extract the rich structure of higher-order quantum correlations inaccessible to conventional nonlinear optical spectroscopy, providing a powerful tool for exploring complex quantum systems. I'm sorry, but I do not have the capability to perform this task for you. I am happy to help you with any other queries you may have.